My name is Heinz Renner. I am responsible for sales and application support for Linseis in Germany, Austria, and Switzerland. I'm in charge with thermal analysis and thermal conductivity, I would say, 25 years now. And the topic for today, for our seminar or webinar, is the Transient Hot Bridge. We have improved a little bit our hot bridge instruments and launched it this year, new models. So the outline for this seminar is, at first, I will give you a short overview about how thermal conductivity can be measured. Then I will show you the THB, how it works, which sensors we have and which sensors can be applied for which individual application. I will present the accessories for the Transient Hot Bridge. I will show you the software, and at the end we will compare the older versions of the THB and the new models. When the thermal conductivity needs to be measured, in principle, there are two different methods. The older one is the stationary methods. For many years, thermal conductivity was measured with plate instruments, which you might know. The working principle is that you have a sample and you have on one side a hotter plate, on the other a colder plate, and you wait. You wait until you have a constant temperature gradient within the sample. The heat flux is measured, and from the heat flux and the delta T, the thermal conductivity can be easily calculated. Stationary or steady-state methods are very accurate. The thermal conductivity can be measured within 1 or 2% uncertainty. The disadvantage of this method is that the measurement takes a long time. So you have to wait until you have a constant delta T. And dependent on the samples, it can take hours, or for very low conductors, even some days. The temperature range is limited. That's a disadvantage. And also the lambda range, the range for the thermal conductivity, is limited. The plate instruments or steady-state instruments are suitable for the low thermal conductivity range. For good conductors, it's difficult because you have to avoid heat loss during the experiment. You have to insulate everything very well, and at a certain point or at a certain thermal conductivity, you cannot avoid heat loss anymore. And by that, the range is limited. The other possibility to measure the thermal conductivity is not to wait for a constant gradient. It is the transient methods measure instantly. So you apply a heat source to your sample, and from the heat source, the heat spreads within your sample, and the measurement starts immediately after you apply the heat source. And you can see here in this chart on the right-hand side that when you measure immediately, you can observe an increase of the temperature versus the time. And the transient methods measure this temperature increase, and the stationary methods measure the delta T at a longer time where the delta T is constant. The transient methods you can divide in, I would say, two different paths. One are the hot wire methods, and the other ones are the optical methods like laser flash or xenon flash. Both are transient methods, so you apply a pulse, a short pulse for laser flash, and measure the temperature increase. The hot wire techniques can apply also a short pulse, but also longer pulses, or the heat can be applied during the whole measurement. To measure the thermal conductivity, various instruments can be used. In our product range, we have optical methods, laser flash, for example, for bulk materials, but also for thin film materials down to the nanometer scale. The laser flash instruments are suitable for every sample you can imagine and in a broad temperature range. This instrument is a heat flow meter. It's a steady state instrument, which is used for insulating materials for buildings or other issues. This is the TIM tester. The TIM tester is also a steady state method, which applies smaller plates compared to the heat flow meter. The TIM tester is used for thermal interface materials, which are used mainly in semiconductors or electronic parts. Here is the thin film laser flash. The technique is more or less the same compared to standard laser flash, but it's for thin films, down to the nanometer scale. For thin films, we have also the thin film analyzer, which works a little bit different. For this instrument, we apply the thin film on a chip, and on that chip there are wires. And it's in fact a hot wire technique, a 3 omega technique to measure the thermal conductivity. And today we have a deeper look on the Transient Hot Bridge, THB, which is a hot wire technique. First instruments have been launched in 2011, and the development process was together with the German Meteorological Institute in Braunschweig, which is called PTB, Physikalisch-Technische Bundesanstalt. And from 2011 on, we sold the THBs worldwide, and it's very spread widely. It's a common instrument technique or measurement method in the meantime. The next slide is showing the measurement ranges for the individual instruments. So you can see on the top the heat flow meters, the steady state instruments are for lower conductivities. The TIM tester, which is also a steady state method, can measure a little bit higher to higher conductivities. The laser flash has a very broad range up to very high conductivities. And the THB has most probably or obviously the broadest thermal conductivity range. It can measure more or less all kinds of samples in the temperature range between -150 and 700 degrees Celsius. The application areas can be very different. So for some applications, you need low thermal conductivities. For example, for building materials to isolate the buildings, for refrigerators or boilers, you need insulating material, and the goal must be or should be to reduce the thermal conductivity. And for these samples, you measure in the range of 0.001 watt per meter Kelvin up to 1. Then a special application where you want to have medium thermal conductivities are thermoelectric materials. Thermoelectric materials are materials when you apply a temperature change to them, then they can transfer the heat energy into electrical energy. And the goal is to increase the figure of merit, which is an efficiency factor. And for this, you need low thermal conductivities. But you need also high electrical conductivity for that. And in theory, it's difficult to have high electrical conductivity and low thermal conductivity. So for the most thermoelectrics, we are in the medium or even low range of the thermal conductivity. Then there are also, of course, applications where you need high thermal conductivity, as high as possible. Brake discs, for example, in cars, or high performance alloys for tools, like these drillers here. They are coated with a thin film layer to get rid of the heat. Then rapid cooling increases throughput in tools for hot forming and injection molding. The heat transport, the fast heat transport is also an issue here. In electronics, you are also looking for good conductors to remove the heat of the CPU or graphical chips or so. And for these applications, thermal conductivity is between 10 and 1000, something like that, need to be measured. The Transient Hot Bridge, as I told you already, is a hot wire technique. And the good thing with hot wire technique is that you get directly, as a result, the thermal conductivity. That's not the situation for the optical methods, for the laser flash, for example. There you get the thermal diffusivity as a result and not the thermal conductivity. But also for the THB, we can measure the thermal diffusivity, and if we know the density of the material from the thermal conductivity and diffusivity, we can calculate also the specific heat capacity, which is quite a useful information. This year, with the beginning of the year, we launched new THB models three different models, a basic one, then an advanced, and the THB Ultimate. With all of them, with all three, you can measure solids, liquids, and powders and paste in the temperature between 150 degrees Celsius and 700 degrees Celsius. The conductivity range with respect to the thermal conductivity, the diffusivity, and the heat capacity depends on which model is used. The measurement uncertainties are the best in the market for the thermal conductivity. For transient instruments, it's below 2%, which is very, very good for thermal conductivity. For the thermal diffusivity, we improved the new instruments and can now measure also with reasonable accuracy below 5%. And the heat capacity, for the heat capacity, we need the density of the sample, and then if we have all these information, conductivity, diffusivity, and density, we can calculate the heat capacity with an uncertainty of around 5% or even better. The setup when you measure solids has to be with two samples, like in this picture. So you sandwich the sensors which you use. I will show the sensor layout later on. And you put on the top and on the bottom a sample. And then you have to put a weight on it or to press it with a press or a suitable device. This is the setup for solids. For liquids, you can just put the sensor into the liquid, but we have also special sensors with a metal frame around it. If you have viscous liquids or pastes, powders, or loose samples, then you use a sensor like this, but with a metal frame around. Typical sensors look like the photographs here. This is the classical THB sensor, with which we started in 2011. It delivers the highest accuracy in the market between 0.1 and 30 watt per meter Kelvin. We can reach accuracies for the thermal conductivity below 2%. Here is the same sensor, but a little bit smaller, with a metal frame around to stabilize the sensor in a liquid or in a paste or in a powder. And this is the so-called QSS sensor, which stands for Quasi-Steady-State. It works different compared to the THB sensor, and it was developed to measure high conductivity, materials with a high thermal conductivity. For small samples, we developed the hot point sensor. The measurement area is here on top of the sensor. We measure here on that area, which is 2 by 2 millimeter. So we can measure quite small samples with it. The Kapton sensors measure up to 200 degrees Celsius in air and up to 400 in inert atmosphere. For higher temperatures, we have ceramic sensors. The layout is the same, but the matrix, it's not Kapton, not a plastic material, it's a ceramic material. We have the THB sensor, the classical THB sensor, the QSS sensor, and also a ceramic hot point sensor. And this ceramic hot point sensor is also very good for liquids because it has a low heating current, and the convection during the measurement in a liquid is quite low. So it's quite suitable to measure liquids as well, but we will see later on. So let's have a look on the individual sensors and how they work. The Transient Hot Bridge, the original THB sensor, works like the classical hot wire or hot strip methods. There are a couple of norms for these methods, and the original methods used a single wire. So you have here a wire or a strip, put it on the sample surface, and then you heat up and measure the temperature increase of this wire. This can be done in two ways. The wire itself can measure the temperature increase because the resistance will change when the temperature increases. But there can be also another wire on a certain distance to this heating wire to measure the temperature increase in a certain distance to the heat source. The disadvantage of these old hot wire methods are that you have edge effects here where the cables are welded or soldered. You are losing heat here, which leads to uncertainties. Then the overall resistance of such a wire, it's quite small, and the effects which you want to measure are the delta T or temperature increase, it's very small, so you need a sophisticated electronics with lock-in amplifiers and stuff like that. So it's yeah, challenging. The goal to develop the transient hot bridge method was to get rid of the disadvantages of the classical hot wire method. And there are some steps in the development to make this possible. So here is how the sensor looks like. This is one heat wire or heat stripe. You can see it is folded a couple of times, and it's what we call meander shape. And this meander shape increases the resistance because the wire is longer, you have a longer resistance, and also the delta, the change of the resistance during the measurement will be higher, so the signal will be higher with a longer wire. But this is not so spectacular. But the next step now, it's very important. It's a big step forward to get rid of the edge effects where heat is lost or dissipated. We developed such a sensor or such a wire here. So we measure the heat loss at the junction points here where the cable is soldered. We can measure that. We can measure it by applying a second part here on a smaller part on the left-hand side. And we can measure the heat loss here at these junctions, at these two junctions, by measuring here the resistance. during the measurement. And when we subtract this one, the smaller part, on this part on the right-hand side of the sensor, then we get fully rid of what is happening here in that part. And the effective length where we measure with that hot wire is only in the middle along this effective length without heat losses. And this is a big step forward, which brings the uncertainty down by a couple of %. And then the next step is not to use only one wire, but 4 wires in one sensor. We have 2 wires on the outer parts of the sensor and 2 in the middle. Why are we doing that? The answer is, if only one wire is used, then before every measurement, the 0 voltage of that wire needs to be measured and subtracted from the measurement. And the 0 voltage is changing with the surrounding conditions, with the surrounding temperature, humidity, and so on. And to get rid of this 0 calibration in measurement techniques, it's a good thing to apply a so-called Wheatstone bridge. So we have here 4 wires and we connect them to a Wheatstone bridge with 4 resistances, 1, 2, 3, 4. And the measurement is the diagonal voltage of this bridge. And it needs to be equilibrated in former times. So some instrument manufacturer, they use also hot wire techniques, and they integrate the Wheatstone bridge in the electronics. And before the measurement, it needs to be equilibrated so that this diagonal voltage is 0. And in our setup, it is self-equilibrating because the bridge is not in the electronics, it's in the sensor. And before the measurement, every wire is at the same temperature. So these resistances depend on temperature, and if all the 4 wires are at the same temperature, then it's equilibrated, our bridge, and then we can start. And this is also a very big advantage because the Wheatstone bridge in the electronics can catch up wrong signals, electromagnetic signals, which can lead to high uncertainties in the worst case. And this setup, which we are using here, gives the method its name. It's called Transient Hot Bridge. Transient is for a non-steady-state method and indicates that it is a transient hot wire technique. This hot stands for hot wire, and bridge indicates that we are using the Wheatstone bridge in the sensor. It's integrated in the sensor. And with all these steps, longer wires, measurement of the edge effect, and integrating the bridge in the sensor, we have the highest accuracy in the market for the thermal conductivity. The measurement itself, it's quite easy. So for a solid, you have to apply your sensor between 2 sample halves. The sensor is acting as a heater and a thermometer at the same time. So for thermal conductivity measurement, you need always a heater, a heat source, and a thermometer. The thermometer can be at a different place or at the same place. In our setup, it's the same. So the wires are heating and at the same time measuring the resistance change, and by that the temperature increase. And when you start the measurement, the heat is transported away from the surrounding sample, and the measurement looks like this here. So at the end, we measure the temperature increase on the sensor surface as a function of time. And this temperature increase is exponential. And when we scale the time axis logarithmic, then we get a linear part of that curve. And we can use that to calculate the thermal conductivity. The theory, it's more, here is the thermal conductivity, it's inverse proportional to this slope of this linear increase. This means, so if you have a good conductor, a metal, for example, then the slope is quite small. And if you have an insulator, it's going faster, that the temperature rise is faster. And the theory, it looks complicated, but it isn't. So this is a typical measurement curve on the right-hand side. The bridge voltage is plotted versus the logarithmic time. And at the beginning, at very small times, it needs a little bit until the heat is transported through the sensor, until the wires heat up. And then, after a while, we see the linear increase of the curve. This bridge voltage, it's directly proportional to the temperature increase. And by theory, you can look on these equations for those people who want to get a deeper knowledge. We have the original publications in which it is described in more detail. But for now, it is okay to know that from the slope, from this delta U at the inflection point here. This is an inflection point which can be seen when the first derivative of this curve is plotted. Then we see a maximum here. At the maximum, we have this inflection point, and the slope is calculated here by the delta of the bridge voltage divided by the delta of the logarithmic time between here and here. And then we have this slope here. It's du divided by the logarithmic of the time, but it's reciprocal. So it's inverse proportional to the thermal conductivity. Here we have the heating current. It's, of course, the curve depends also on the heating current which we apply and on the thermal conductivity. And so everything is constant. These factors here are constant. The calibration constant is constant. And the current, it's also constant during the measurement. And so we need only to calculate the slope, and then we can calculate the thermal conductivity. We can also calculate the thermal diffusivity, and this diffusivity is calculated at the end of the measurement when the maximum here is arrived, and then you can see that the first derivative goes down here. So this means the slope is getting smaller, and to reach that time until the linear slope, or this more or less constant slope, is left, and where we go to a transition to a steady state, this time, from this time here somewhere, we can calculate the thermal diffusivity. Specifications of the THB sensors. So it's a patented sensor. It's suitable for fast and high accuracy measurements. We will see later that the measurements need only a couple of seconds, and the accuracy it's very high. And thermal conductivity, diffusivity, and the specific heat can be measured. The thermal conductivity range for these THB sensors is up to 30, from 0.02 around to 30 watt per meter Kelvin. In this range, we have the highest accuracy, below 2%. And the Kapton sensors can measure up to 200 degrees Celsius. If a furnace with inert gas atmosphere is available, they can withstand also 400 degrees Celsius. And it can be applied for solids, liquids, and pastes. But for liquids and pastes, only the pure sensors without a metal frame around it, if the viscosity is not too high. If you have liquids, powders, or pastes, or with liquids with a higher viscosity, a metal frame needs to be placed around the sensor to stabilize it. And then the specifications are the same. For a higher temperature range, the ceramic sensors can be used. The thermal conductivity range is not as high because the time constant of the ceramic sensors is longer. So the time resolution is not so good compared to the Kapton sensors. And that's the reason why we can measure with the ceramic THB sensors only up to 10 watt per meter Kelvin. But they are suitable also for solids, liquids, pastes, and powders up to 700 degrees Celsius, beginning at minus 150 degrees Celsius. To measure higher thermal conductivities, we use the so-called quasi-steady-state sensors, QSS sensors. And with these sensors, we eliminate the time constant. So the setup of the sensor is a little bit different. We have a heater here in the middle. That's the heater. Then we have a thermometer, a PT100, at this position, and a second one which is which has a bigger distance to the heater. And we measure until we have a constant delta T between R2 and R3. So it is a steady state method because we apply a heating current and then we measure until we have a constant delta T, a constant gradient. The resistances or the thermometers R1 and R4 are needed to build the Wheatstone bridge in the sensor. as we see here. So, and typical results look like that. T1 is measured and T2. So T1 comes from this resistor, which is nearer to the heater. So it goes up faster because it sees the heat from the heater earlier. And T2 comes from the resistor R3. And then the difference between the T1 and T2 gives delta T, and the measurement needs to be done until delta T is constant. And from this delta T, with the knowledge of the heating power or the heating energy, lambda can be calculated like in any other steady state method. So lambda, it's directly proportional to the heat energy divided by delta T. And the rest is a constant factor. This method is very suitable for good conductors. Practical, the whole range of materials can be measured. It goes up to copper and even further. The specifications are listed here. So it is designed and suitable for high thermal conductivities. It combines the advantages of the steady state and transient measurement techniques in one sensor. The uncertainty, it's quite good for thermal conductivity devices. It's not as good as with the THB sensors, but it's still below or between 5 and 8%, which is better compared to laser flash, for example. The range, it's practically all. It's the whole range of thermal conductivity you can measure. The temperature range it's the same compared to the THB sensors. It's suitable for solids. It could be applied also for pastes and liquids, but it makes no sense because the THB sensors are better for pastes and liquids and powders. The ceramic one goes, it's limited with respect to the measuring range. The ceramic QSS sensor, which can measure up to 700 degrees Celsius, can measure up to 100 watt per meter Kelvin. Then the third kind of sensor which we have in our product range, it's a hot point sensor with a small measurement area, 2 by 2 millimeters. The theory behind it's a little bit different, but at the end you have an equation where the delta T, so you measure, it's a simple thermometer, it's like a PT100. You measure the temperature increase during the measurement when you apply or during the application of the heating current. And this delta T increases with this here, with 1 over the square root of the time. And by that, you plot the measurement curve, the delta T, which you measure, you plot it. Show this again. This T star is 1 over the square root of time. And then you get a curve like this. So long times are in this direction to the y-axis, and short times are here. This is the beginning of the curve. It needs a little bit until you get a stable signal until the heat goes through the sensor and reaches the sample. And after a couple of seconds, you see a linear increase here. And by theory, from the intercept of this curve with the y-axis, you get a delta t. And with that delta t, here, this is the intercept. This intercept, this delta t, it's inverse proportional to lambda. So if you have that, and if you know the heating energy, then you can calculate lambda from this intercept. The slope of that curve depends on the thermal diffusivity, alpha. So if you calculate the slope, you can calculate also alpha, the thermal diffusivity. The specifications of the hotpoint sensor, it was designed mainly for small samples, down to 2 by 2 millimeter. It can be used also for anisotropic samples, which is quite useful. The uncertainty is between 5 and 10%, and the measurement range of the Kapton hotpoint is between 0.01 and 30 watt per meter Kelvin. And for the hotpoint ceramic, for the ceramic hotpoint, it's 0.01 up to 5 watt per meter Kelvin. The accessories which we can offer to you is quite broad in the meantime. So we have a couple of temperature accessories. For many applications, it's okay to get data between -20 and let's say 50, like it is in the real world, in our surrounding. So for building materials and other applications, that's quite fine. And we have designed a Peltier-controlled furnace, which can reach these temperatures easily and fast, and it's cost-effective. For a little bit higher temperatures, we developed a cartridge heated furnace, which can reach 200 degrees Celsius. And then we have also high temperature furnaces. We use the furnaces, or we can use the furnaces from our other equipment which we manufacture, like dilatometers or thermobalances. And the high temperature furnace can go up to 1000 degrees Celsius, but only 700 can be used right now because the ceramic sensors withstand only 700 degrees Celsius. Then we have a low temperature furnace, which is cooled with liquid nitrogen. So it can reach temperatures down to -125 degrees Celsius and up to 500 degrees Celsius. We have also a furnace in which you can measure under controlled humidities between 2 and 98% relative humidity, which could be also interesting for some of you in the field of in the construction, building materials, and so on. Then we have developed some devices here on the right-hand side to apply a defined pressure on the sample. The pressure is measured also because you have to bear in mind that when you have compressible samples and you apply a pressure, then you change the density of your sample. And you can measure with these devices under defined pressure, and you know then also you can calculate back the volume, and then by the pressure and volume, or by the volume, you can calculate back the density, and at the end you get thermal conductivities as a function of density. Some words to the software. We made the new software more easily to operate. We have now, so it's very straightforward. When you connect a sensor, then the sensor is automatically detected and shown here in the software. And then it's more or less a one-button solution in the software. You have some menus here, but when you click, or these hooks here, when you activate all these hooks, then the correct measurement parameters are found by the instrument. There are two measurement parameters, the heating current and the time. And both are found now automatically. So the hook needs to be activated here to find the optimum heating current and the correct time when the measurement can be stopped. Here, just the sample name needs to be typed in that line here. If the thermal diffusivity should be measured or calculated, then activate the hook here. From the diffusivity, some other properties can be calculated, like the thermal penetration of the heat into the material during the measurement, the specific heat capacity. If you activate the hook here, you need to type in the density here, because you need the density to calculate the specific heat from the diffusivity and the conductivity. The effusivity can be also calculated from the thermal diffusivity. And that's it. Just press a button here on Start Measurement, and then it needs a couple of seconds, 3-4 seconds, until the instrument finds the optimum heating current with a pre-test, and then the measurement is performed and you get data like that here. So on the top of that chart, you see the raw data. It's the bridge voltage and the temperature increase as a function of time. And here on the bottom chart, it's that the time axis is changed to the logarithmic scale. And then you can see the blue curve here, it's the bridge voltage, which increases linearly. And the black curve is the first derivative of the blue curve. And you can see a maximum here, which indicates the inflection point here. And at this inflection point here, the thermal conductivity is calculated. You can do multiple measurements or single measurement. It depends on what you want to do. In this example, 3 measurements have been performed and the average values have been calculated here. You see here a button, Create Report. When you press that button, you can choose a template. We have Word templates, HTML templates, or simple text templates. You choose one, you can, then you get a report file like here, and you can edit the template like you want. You can change the logo here and the rows or whatever. I will show you now a real measurement, which we did with the THB Advanced in our lab. So I start the measurement and you will see it's the sensor is found now by the instrument. Here, the sample name, it's a plastic material, is typed in. The hook is set for automatic measurement and measurement is started. It took 2 or 3 seconds to find the optimum current. And now the measurement is running, and the instrument detects automatically the end of the measurement when enough data are there to stop it. And that's it. And now you see after 27 seconds, you have the result 0.1933 for the thermal conductivity, watt per meter Kelvin, and for the thermal diffusivity, it's 0.1217. And the temperature here, it's also measured with the sensor. So the measurement started at 22.2 degrees Celsius, and the temperature increase on the sensor surface during the measurement was 4.17 Kelvin. The calibration of the sensor normally it's not necessary because it's an absolute method, the transient hot bridge. But it can happen that the sensor gets changed by pressing too much, or if you have a rough surface on your sample, that the wires get damaged a little bit, then the resistances of the sensor might change, and you need to re-measure the resistances. And this can be done also very easily in the software. It's automatically done within 1 to 3 minutes. And you choose here from the menu sensor calibration, and then you can choose if you want to calibrate the thermal conductivity and diffusivity or temperature. Then just click, here are the values for the resistances. These values will be changed during the calibration. You type in the surrounding temperature here in the next window, and then just choose from the list. If you press the button here, a list pops up with calibration standards. In this case, BK7, that's a glass, but also PMMA or metals can be used. The values, the literature values are listed here, and after that, so just press start calibration, and then the calibration is done automatically. It's the same with the QSS sensor, the same procedure. Now, at the end of the presentation, I want to show you a comparison of measurements between the older models, especially the THB1, which is widely spreaded in the community, and the new THB Advanced. This might be interesting for those who have already a THB, THB1, 100 or 500. So we measured a couple of materials. We measured a plastic material, PMMA, titanium, copper, and a zinc material. And for the PMMA, we used for both instruments the THB sensor, and for the higher conductors, for the metals, we used a QSS sensor. We took 2 sample halves, put the sensor between the 2 sample halves, and pressed it with a press. You need around 0.5 bar contact pressure, which is around for this sensor size. It's equivalent to around 3 or 4 kilogram of load on that setup. So the first measurement was done with PMMA. So this can look familiar to those who have an equipment. You see the bridge voltage, blue line, the pink line, it's the first derivative of the blue line, and the red line is the temperature increase. And from these data, you can calculate the thermal conductivity and thermal diffusivity. The same signal is here on the bottom part of the new instrument measurement. You see here the blue line, bridge voltage, the derivative of this blue line. And here on the upper part, the red line is the temperature increase during the measurement. And when we compare the data, we see both instruments are very good for the thermal conductivity. And with the older generation of instrument, we always had the problem that the thermal diffusivity could be measured, but with high uncertainties. In this application with plastics, it's 25%, which is too high, I would say. And with the advanced instrument, the measurement is faster. The accuracy, it's also very good for it's in this case 3 measurements have been performed, and on average, so it's 0.192, it's 1%, within 1% of the literature value. And now you can see that this is a good thing, a very good thing, that the alpha, the thermal diffusivity, we can measure now due to the much better time resolution of the experiment, also within 1% for plastics. Then the next example shows titanium, which is a metal at the lower end of the thermal conductivity range. The result, or the measurement, looks a little bit more noisy because the signals are getting smaller the higher the conductivity is. And when we calculate the data, we fail for the THB 100 to get the alpha, the thermal diffusivity. It's not possible because the experiment is already too fast for that device. But lambda can be measured accurately. So for lambda, the older instruments are quite okay. And you see here also the alpha for the new THB Advanced, it's 9.2. It's within a short uncertainty. It's a very good result. Then the next one is zinc. Then for the THB 100, we are at the limit already. Originally, the THB 100 was specified up to 100 watt per meter Kelvin. That's the reason why it was called 100. And zinc, it's above 100 watt per meter Kelvin. And you see the curves, the measurement curves are quite noisy. So the error, it's probably very high here already. And with the new one, the advanced instrument model, quite nice curve we can reach here. But still, it's okay, I would say, for the lambda. For the THB 100, it's still good, 2% uncertainty or deviation. For the THB Advanced, it's better, it's 1.5%. And also we can measure alpha, but it's starting already to get higher in uncertainty. But at least we can measure it, which was not possible at all with the THB 100. And then we go to copper. You can see a plot from the measurement which we did. We did 3 measurements with pure copper, 99.999% copper, and we can measure the thermal conductivity on average 414 The literature value is 400, so it's a good accuracy. It's a quite nice result. With the THB 100, it is not possible at all to measure copper. For the thermal diffusivity, we are a bit off, because now we are with this advanced instrument already above the limit, above the time resolution. With the THB Ultimate, it would be possible to measure thermal diffusivities also for copper with an accuracy of 5 to 10%. So, to conclude, what we have seen during these presentations, the benefits of the new instrument models, I will summarize shortly. So when we do the measurement with the THB sensors, the THB method is in fact the most accurate instrument on the market to measure the thermal conductivity. There is no other instrument available which is more accurate. It is a one-button solution. So this means it's fully automatic. You need no special experience to operate the instrument. No experienced staff is necessary. Everybody can learn it within a couple of minutes to operate the instrument. And this leads to also good results, because the errors caused by wrong measurement parameters are eliminated. The results we get are the thermal conductivity and the thermal diffusivity. Both can be measured with low uncertainties. And if we know the density of our sample, we can calculate from these two values also the specific heat capacity. So we can use it as a calorimeter as well. We can measure small samples. That's also a benefit of this method. The smallest possible sample is 2 by 2 millimeters. And that's, I don't know another instrument on the market which can measure such small samples. Then the measurement you have seen is quite fast. It's within seconds, below 1 minute. And it's with a special sensor. I didn't show it today, but we have it. It's a single sample sensor which you put on the sample. You need only a surface, and you can put the sensor on any sample and measure. You need not to cut out something and prepare the sample. Just put the sensor on and measure. It's not as accurate as with the double sample method, but it's within 10%. The instrument itself, it's very small. It's around 20 by 20 centimeters. So it fits in small places, because sometimes lab space, it's an issue. But this instrument, it's really small and light. So that's it for today. Thank you very much for your attention.